So not only is this section over increasing and decreasing, which I think we've covered to its full extent, but it's also over relative extrema. So that may seem a little intimidating at this point, but basically it's just fancy wording for finding maximums and minimums on the graph. So if you ever have a homework or a quiz or an exam problem that asks you for relative extrema, it's basically asking you to pick out the maximums and the minimums on the graph. So let's start by doing this visually. Let's look on our graph and let's see if we can pick out the high and the low points. Well, the most prominent point is this one right here. Of course, this is a high point. When we're talking about maximums and minimums, we care about how high and how low they go. So we have a high value at 8. So our first one that we're going to pick out is the max value. We have a max value at y equals 8. Now, sometimes we care when that happens, and so that's when we pick out the x value that goes with it. And so that's happening when our x value is equal to -2. Now, you might be tempted to put this in ordered pair notation, and sometimes that's fine, but a lot of times when it's just asking for the max value, it's just asking for the y value that goes with it. So I would just try and always answer it in the y value unless it asks you specifically what it is in ordered pair format. Now, that's not the only high point on this graph. We also have a second high point at this right here. So the y value of when that's happening is 2, and if you care, you can also tell us when the x value is, and so that x value is 1, or it comes from the ordered pair of 1, 2. But remember, most of the time, it's just specifically asking for the value, which is the y value. Now, that seems to be all the high points on the graph, so let's switch to minimums, any low points on the graph, and we have a low point right here. So our low value is the y value of 0, and the x value of when that is happening is also 0, or in ordered pair notation, it's 0, 0. Now, maximums and minimums are really easy to find if you have the graph to reference, but what happens if you don't have the graph to reference? Is it just gives you the function. The specific way to find this also answers the question as why it is in the increasing and decreasing section. Because anytime a graph switches from increasing to decreasing, or if you think about it visually, anytime our graph goes from going up from left to right to going down from left to right, that's going to give us a high point on the graph. So anytime our slope or our derivative switches from positive to negative, that's going to tell us that we have a maximum point on the graph. Because if we look at this here, we're going from increasing to decreasing. And so that creates this maximum point on this graph. And then also over here, we're going from increasing to decreasing. And that creates a maximum point on the graph. To find a minimum, then, we just flip-flop it. If any time our graph goes from decreasing to increasing, or if it's going down from left to right to up from left to right, that's going to create a low point on the graph, which is going to create a minimum value. So anytime our slope or our derivative switches from decreasing to increasing, that creates a minimum on the graph. And we can confirm that with the middle point here. It's going from decreasing to increasing, so therefore we have a low point on our graph right here. So now that we know the basics of the relative extrema, or maximum and minimum, let's do this on some other examples. So here in this graph, we want to find all critical values, and then we want to classify them as maximum, minimum, or neither. Now, when we found our critical values before, it's when our derivative comes up to be 0. So when our derivative is equivalent to 0, that gives us our critical values. So basically, we want to find any places on the graph where our tangent lines would be horizontal. So that would happen Here, this would give me a horizontal tangent line. Here, 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 and here. So all of these are critical values on this graph. Now we want to classify them whether they are maximums, minimums, or neither. Now we don't actually want to give the maximum or minimum values on this place here. We just want to figure out what kind of relative extrema they are. Okay, so let's just split them up into whether we have maximums, whether they are minimums, or whether they are neither. So I'm going to do this from left to right. So my very first x value here looks to be -5. We see that's a low point on the graph, so that's going to be a minimum when x is equal to 5. My next critical value of here is a high point on the graph, so that means we have a maximum value at 3. Next is maybe a half value when x is equal to 1/2. We see that's a low point, so that is x is equal to 1/2. Next is the only time where I don't have a low or a high point, but I do have a horizontal tangent line here. So this critical value is neither a maximum nor a minimum, so that's why it goes into my other sort of category here. Now, a lot of the times the neithers I like to think of as plateaus on the graph, where my graph flattens out, but it's neither a high point nor a low point there. And my last one here, a little bit above 6, let me do 6.5. We see that's a high point there, so I would classify them as maximums. So we found all critical values on the graph where my graph flattens out or where I have horizontal tangent lines, and then I've put them into the categories of maximums, minimums, or neither. Now again, this one gave you a graph, so what happens when it doesn't give you the graph and it gives you a function instead? To find these, you're going to be doing the exact same steps that you would be doing to finding the increasing and decreasing function, the same steps that we did in our last couple examples. Then when we end up with our sign chart, we look to see whether our sign chart is going from positives to negatives, which confirms that we have a maximum, or whether our sign charts go from negatives to positives, which tell us we have a minimum. Okay, so back to the last two examples that we have here. I just picked out my sign chart or my number line and my final answer. So anytime my graph switched from a positive to a negative, that creates a high point on my graph, and that tells us that we have a maximum. So the maximum is happening when our x value is equal to -2, and we just need to do some extra work to figure out what that maximum value actually is. Okay, and again, anytime our graph switches from decreasing to increasing, that creates a low point on our graph, so that tells us that we have a minimum value. So our minimum value is happening when our x value is equal to 1. So we just have to do some extra work to figure out what that minimum value actually is. Well, these are found by just using the original function. We just need to figure out what our y values are if we were to substitute our x values into this function. So to figure out where my maximum value is, I just need to figure out what f of -2 is. So let me plug -2 into that function. So when I simplify this here, that gives me the y value is equal to 13. So my maximum is happening when y equals 13. To find the minimum value, I'd be doing the same thing, just plug in 1 to my function. And when I simplify that, that gives me the value of -14. So that is where my minimum value is at. And we can confirm this by looking at the graph. So I know that I should have a maximum value at -2, so let's confirm that I have the right y value. So if I type in trace, and I type in my x value of -2, that gives me my y value of 13. That does confirm that I have my maximum value there. I also know that my minimum value is happening at 1, so if I type in 1 and hit enter, That tells me my minimum value is happening at -14, and that confirms that that is, in fact, a minimum on my graph. So the graphing calculator will always confirm all of these answers for you. You just have to do a little bit of work ahead of time. Now let's do it with this function here. So again, anytime it switches from positive to negative, that tells us that we have a max value. So we have a max value when your x value is equal to 0. And so we just need to figure out where that max value is at. And we have a minimum value when your graph switches from decreasing to increasing. So that's happening when your x value is equal to 4. So here we have a high point, my max value at 0. Here I have a low point, my max value at 4. Now, 2 is a vertical asymptote. So it is not considered a critical value, and it's not considered a relative extrema by any point. It's just an exclusion from the domain. So I would not list 2 as any sort of relative extrema here. Okay, I just need to figure out what these are if I were to substitute my x values in for them. So if I figure out what g of 0 is, 0 squared over 0 minus 2, that gives me 0. So that tells me my maximum value is at 0. And my minimum value is when g is equal to 4. So 4 squared over 4 minus 2, which gives me 16 over 2, or 8. So I have a minimum value at 8. Now, it might seem a little confusing, why is my max value smaller than my minimum value? But we can always think about this in reference to the graph. So let me pull the graph back up. We can see that I had a high point at 0, and I had a low point at 8. So it doesn't matter that my low point is actually higher than my high point. It just matters in reference to the graph. So I've shown you how to find maximums, minimums, or relative extrema from the critical values of the graph. So in the next section, we're going to be doing full examples of ones that we haven't already found increasing and decreasing for.